You will not there. Firstly, many thanks to the organizers of the program, this reunion and the workshop. We are all benefiting from your hard work, so thank you very much. So this is joint work with three of my colleagues, Laure Daviaud, Karoliina Lehtinen, and Thejaswini. So Laure is at University of East Anglia at the moment, Karoliina CNRS in Bordeaux, and Thejaswini is a postdoc at IST Austria. She will be on the job market in a few years, so hire her.
You have to write a reference letter.
I will, yes.
Dr.
So this talk is about a definition and about two theorems. So the concept that I'd like to tell you about is that of an attractor decomposition. Most of you will be quite familiar with it, but I hope to argue on two case studies of applications of this notion that it's worth taking a closer look at the structure of those attractor decompositions. So what is the basic object we will be looking at, working with? It's parity graphs. So they are graphs, directed graphs, so it's vertices and edges. And every vertex, let's say, has a label given by that function. I will call it a priority. That label will be a priority of that vertex. And those priorities will come from some initial fragment of positive integers. Okay? What really matters, as you are going to soon see, is that there is a hierarchy, alternating hierarchy of what's good label and what's bad label. We happen to, for historical reasons, think about even and odd numbers, but really what's the crucial issue here is that we have good ones, then better, higher, bad ones, and then even stronger ones that are good ones, and so on. So I will assume about such graphs that they can be either finite or infinite. So no assumption about whether they are finite or infinite. But what I will assume is that for simplicity and without loss of generality, that from every vertex, there's at least one successor. So that it will follow from this that all maximal paths in such graphs are infinite paths. Okay? I will say that an infinite path, a maximal path in such a graph is good, I will say even, if the highest priority, highest vertex priority that occurs on that path infinitely many times is even. If the highest vertex priority that occurs infinitely many times on that path is odd, that will be bad. Okay, so even is good. I will say that a graph is even, and you should think of such a graph as maybe a graph of a winning strategy in a parity game, if all paths are good, if all paths are even. So on every path, the highest priority that occurs infinitely many times is even. Here's the definition I was mentioning earlier. So far, no. So here's the definition. If you have ever worked on parity games and maybe analyzed one of the algorithms for parity games, then this will look familiar. Okay, so what is an attractor decomposition of a graph? I will later try to convince you that an attractor decomposition of a graph exists if and only if the graph is even, which means that all paths are good, or maximal or all infinite paths are good. So a decomposition is simply a partition of the set of vertices in the shape like you see on the screen. So firstly, we have this top part where this set H is simply the set of all vertices in this graph which have this maximum priority D. And I will assume without loss of generality that the priority D is even. Okay, so that's the strongest label, and it's even, so it's good. Now, what is A0? A0 is going to be the set of vertices such that all paths starting from those vertices eventually, after a finite number of edges, end up hitting set H. So I call this set the attractor to H. Okay, so once again, it's the set of vertices from which all paths lead to H. And then There will be an edge which will get us somewhere back into the graph, no matter where. Okay? So I call this the top attractor of the attractor decomposition. And then we will have a number of side attractors, each of which consists of two sets, again disjoint. One set that D1, D2, and so on, will have the following restriction. All the vertex priorities in those green sets must be bounded by D-2. So D-1 is odd, remember, by our assumption. That's bad. So in each of those parts, D1, D2, we cannot see any of those highest bad priority. Now, what are A1, A2, and so on? They are, again, attractors. I will tell you in a minute. So A1 is the attractor in the graph without the top bit to D1. Right? So all paths that originate in A1 eventually hit D1. Now, if we zoom out and look at the whole picture, it may happen that some edges go up, and we allow that. Okay? But no edges go right across that boundary. Okay, that's a restriction we impose. So maybe that's the difference, right? We cannot move right in that picture. Again, here we will have another set. Here the priorities are again restricted to be at most D-2, so no highest bad odd priority. A2 will be the attractor to D2 and so on, right? So the picture is that in the bottom part, we can always move left. That's allowed. There may be edges that take us directly from here to there, but we can never move right. So these are hard boundaries that we must not cross. Okay, these are the, yes? No guarantee, but it's allowed. Okay? So edges like that are allowed. So edges up are allowed, edges to the left are allowed always, but edges to the right are not allowed. So these are the conditions of an attractor decomposition. And then there is an extra condition that each of those green sets, D1, D2, and so on, are themselves attractor decomposition. So they can be decomposed in an inductive manner, right? So now the top priority there is D-2 rather than D. And then they have a top attractor and a collection of side attractors. It's a hierarchical structure. There was a question. No, D1 is not empty.
Let me see if I understand correctly. So take D1. D1 will be all the nodes that have at most D2, D-2.
Mm-hmm.
But if they reach a node with D-1, then it's going to be in A0.
That's right.
And then from there, they must move to D.
That's right.
Okay.
So that's an attractor decomposition. I claim a graph is even, so it has only good paths, if and only if such an attractor decomposition exists. Question.
In this hierarchy, at the first level, the D1 is the H. So you said that the D1 must have an attractor decomposition, and then the D1 plays the role of the H.
So no, so D1 will have an attractor decomposition. What will be the shape of the decomposition? Well, it will have a top attractor consisting first of the set of vertices of priority D-2, its attractor and collection of side attractors. Right, so one direction in this fact is easy. If a graph has an attractor decomposition, then the graph is even. Why is that? Yes, a question.
So this is a attractor decomposition of one pair, right?
Yes, that's right. So it's an attractor decomposition of a, say, winning strategy or one player game. Mm-hmm. So one direction is easy. If we have an attractor decomposition, then the graph is even. Why is that? Well, either we will hit the top attractor infinitely many times, see the top even priority infinitely many times, and hence the path is good. Or we will eventually have to settle in one of those green parts, and thereby inductive hypothesis that the path must be good. Okay. So that's the argument. And I'm going to show you the other direction in a minute.
But if we stay, let's let's take D1. Let's suppose we get stuck in D1.
Yes.
D1, just you know that the color is less than less or equal to D minus 2.
But it has an attractor decomposition itself.
Oh, because
So it's a requirement for the definition of attractor decomposition that these sets, these parts have attractor decompositions themselves.
Yeah.
The whole thing is actually a tree structure, right?
Yes, that's where we are going to. So that a hierarchical structure of an attractor decomposition can be abstracted into a tree, defined in the obvious way, right? So the tree of the whole attractor decomposition has a corresponding tree whose root has children, which are roots of sub-trees, which are the trees of the attractor decompositions D1, D2, and so on. Okay. So that tree will be node of height at most d half, right? Because each time we step from a node to its child, we reduce the top priority by 2. Okay. Sometimes I will not discuss it in great detail here, but when running algorithms, this actually can be seen as a data structure which underpins some algorithms for solving games, party games. And there it's really particularly useful to view this decomposition as a labeling of vertices in the original game or graph by nodes in such a tree. Okay, so that's how I'm going to write attractor decompositions from now on. So there's one thing I wish you remember from this talk. It's this. And that's this view, which I want to promote, that it's useful to measure the structural complexity of a parity graph or a parity game as the structural complexity of the tree of one of its attractor decompositions. Okay? So I hope I will convince you by the end of this talk that it's a useful view.
What does mean here? Mean on what? What are you minimizing?
I will elaborate later.
Okay.
Right. So here is so we've covered the definition. Yes.
You're analyzing, in a sense, Zielonka's algorithm, right?
So yes, Zielonka's algorithm or McNaughton-Zielonka algorithm produces attractor decompositions so it produces them explicitly. But I would argue that essentially all parity game algorithms, in one way or another, more explicitly or less explicitly, actually produce attractor decompositions. Okay. Right. So now for the first theorem that I would like to show you, first case study where we try to make this proposal concrete. It's to do with alternating parity automata. So they are parity automata. We have acceptance conditions which are like in those parity graphs that I discussed, right? So we have infinite paths in runs, and they are good if the highest priority that occurs infinitely many times is even. So we label states by these priorities. We have a set of states, initial state, alphabet, a transition relation or function, however you want to formalize it. Maybe what matters, I will not tell you exactly how those automata work, but what matters is that their runs can be seen as directed acyclic graphs, where we have these layers which correspond to essentially the position in the word that we run such an automaton on. Each layer has vertices which correspond to unique states. So hence, each of those layers has size bounded by the number of states in the automaton. And an accepting run will be a suitable graph on such a structure which is even, which means that all paths in it satisfy the parity condition. So here is a theorem of Moshe and Orna from some time ago, from last century. It was known even earlier that alternating parity automata are not that powerful because you can in fact recognize all regular language. They only recognize omega regular languages, but in fact you can reduce the number of priorities used in the acceptance condition to 2, even more. It suffices to have an acceptance condition which is weak, which is both Bichu and Kobichu. And I think the original argument involved a double exponential blowup, and Moshe and Orna had this construction which translated from parity automaton with d priorities down to, in fact, better than 2, weak, with a blow-up that was only singly exponential, and in the exponent we only had the number of priorities. So our result, that's a result with Laure and Karoliina, is that you can do this translation with a blow-up that is only quasi-polynomial, where in the exponent we have log, actually base 2, to be precise, of the number of priorities. And if the number of priorities is logarithmic, then it's actually polynomial. So how did we get there? The key insight in our construction is that if you take an accepting run of an alternating parity automaton with d priorities, in fact, it doesn't matter how many priorities there are there, it has an attractor decomposition, right? So that graph, that infinite DAG, it has an attractor decomposition whose tree has at most n leaves, where n is the number of states. Okay, so such run DAGs, accepting run DAGs, have small attractor decompositions. So every talk should have one joke and one proof. Right? So that was the joke. Let's take a look at the proof sketch. How do I construct such a decomposition? Let me take the set of, right, so I have this run DAG. Let me take the highest priority D even. Let me take this set H to be that set of vertices of highest even priority. Now let A0 be the set of vertices that have finitely many descendants in the graph without H. That's exactly the kind of argument that Moshe and Orna used. I claim this is the attractor, the top attractor. Okay. Now note that in the rest of the graph, which I call G0, now every vertex has at least one successor, right? Because if it has none, then it would be in A0. Now, how do I pick D1? So here's one particular choice. I told you that I will show you the opposite direction. If the graph is good, then it has an attractor decomposition. That's one possible choice. There may be others. So there are potentially many different attractor decompositions if your graph is good. One good choice, kind of maximalist choice, is take all vertices that are what I call D-1 safe. What do I mean by that? That means that no path from those vertices can reach a vertex of priority D-1, which is bad odd, high odd. Why is this set D1 non-empty? Question to you.
And what was G0?
G0 is the part without the top attractor. Okay, I have to rush, so let me tell you, right? If this set was empty, that means that everywhere in G0, I have a path that leads to priority D-1. But if that's true, then I can keep going and construct a path, maximal path, in which D-1 occurs infinitely many times, but I don't have any Ds, so it will be bad. But I assume that the graph was good. Okay? Then I take A1, which is exactly like A0. Now I take simply the set of vertices with finitely many descendants in the graph G0 without this. That's the attractor, and I continue. Okay? So that's how we construct an attractor decomposition. Now, why is it small? Why does it have at most, and why does its tree have at most n leaves. It's a bit subtle, but not too difficult. We can argue because D1, D2, D3, and so on, they are disjoint, and they all have this property that every vertex has a successor. We can define suitably define a concept of width of those graphs, and those widths are kind of additive. So if I want to count the number of leaves in the tree of this attractor decomposition I have described, it's equal to the number of leaves in its sum of the numbers of leaves in its subtrees. That's trivial. But then inductively, you can show that that must be smaller or equal than the sum of the width of those graphs. That's, again, slightly subtle, but easy argument shows that this is smaller or equal than the width of the whole graph, because these subgraphs were disjoint. But that is bounded by n, because every layer had at most n vertices. Okay, so the tree of that decomposition we have constructed is small. It has at most n leaves. All right, so now we are ready to prove the theorem, which is that if you give me a alternating parity automaton with d priorities, with n states, then I can construct another alternating parity automaton, now with only 2 priorities, 1 and 0, and whose size will be this. So what's the idea? The idea is to kind of mimic what the original automaton is doing. So that's what I summarize here as this new automaton guessing an accepting run. So it's guessing this accepting dog. Now the next idea is to have another component in the automaton which simultaneously is guessing an attractor decomposition. So for every vertex, it will guess a node in that tree that we know exists and is small. But now you may say, how does the automaton know which tree? Right? So those are small trees, but there are exponentially many of them, or maybe even more. Yeah? So the idea is to, instead guessing that tree and nodes in that tree, to guess nodes in what we call a universal tree that has as its isomorphic copies all such small trees with at most n leaves and of height d half. Okay, and that's enough. So in a way, the components, the states of the new automaton are states of the old automaton and leaves in such a universal tree. Okay, and then we can use a result which we have proved together with Ranko Lazic earlier, that such NH universal trees, right? So trees that have as copies, which have as copies inside it all trees with at most n leaves and of height h, exist and have this size. And that was kind of the technology that provided one lens on this groundbreaking result of Buck and colleagues, which has established that it is possible to solve parity games in polynomial time, in quasi-polynomial time.
But the attractor decomposition was really essentially already implicit in the 98 paper, I believe, no?
So you constructed attractor decompositions for the special case,
Yeah.
With 2 priorities.
Yeah.
Right? For the Kobishi case, in fact.
Yeah.
And then the attractor decomposition is kind of the tree of such an attractor decomposition is the root and a bunch of children.
Yeah, yeah. So the improvement is not the attractor decomposition,
Yeah.
it's the way to implementing it using this new data structure.
But I would argue it was not clear that there is a tree structure in your
No, we
construction.
didn't talk about the tree structure. We just did attractor
Yeah.
decomposition. But there is an implicit attractor
So
decomposition there in the
you know,
proof.
what you do is an inductive construction where at every step you reduce the number of priorities by 1. But I agree that
It's an attack. It's very
analogous ideas.
It's very similar attractor decomposition.
Analogous
but,
ideas are
but,
there.
but it didn't have the tree structure.
That's right. You could.
And I think the tree structure now give you the better bound.
Yes. Well, you could argue. Sorry, I got lost a bit here. You could argue that what you are doing in that earlier work is using a universal tree, which is kind of trivial, right? So it's a tree of height d half,
Yeah.
with every vertex having n successors,
Right.
n children.
Yeah.
And that has exactly that size.
Yeah. Yeah.
Whereas there are smaller universal trees that
Right. Right.
that are enough. Right. So that's one theorem. Let me tell you about another one. Before I do, I have to tell you about this beautiful construction of Karoliina Lehtinen from 2018, who saw the great result of Buck and colleagues, Kaluda, Jane, Hussainov, Lee, and Stefan from 2017 about quasi-polynomial time algorithm for party games, and tried to jump on the bandwagon by saying, oh, I want to explain in a different way or get a different algorithm that is also quasi-polynomial. I really like that one because it's quite original. So the idea is to construct, so Karoliina proposed to consider so-called register games. I formalize it here as certain transducer, which has as states k-tuples of priorities in the original party game, let's say. Okay? So we have priorities between 1 and d. Now we maintain tuples of such priorities. They are ordered. So if we call this register 1, this register 2, this register 3, this register 4, then they are non-decreasing in this order. Now that automaton that has states like that, the transducer that has states like that, what it does is that it consumes priorities and outputs priorities in different range. So it consumes priorities in range from 1 to d, but it outputs priorities in the range from 1 to twice the number of registers. How does it do so? Let's take a look at an example. So imagine we are in this state. We encountered priority 6. So now we are going to update the registers. How? Well, we will look from the right to the left, and we will replace the ones, the priorities that are smaller than the current one by the current one. Okay? But the ones that are larger than the currently consumed priority will stay the same. It's kind of a hierarchical set of registers which remember something about the past, what priorities have occurred recently. Okay. Then there is another step, and that's what I call control. So you could see the input of such a transducer as pairs, a number between 1 and d, and then the number between 1 and k, so a register number. But the way we are going to use it is that this will be really the input, and this will be kind of control. So once we get that control, say number 2, what it does is that it's now going to look at the second register, because that's 2. If this entry there is even, what it will do is that it will output 2 times the number of register as a priority. 4. If that priority in the second register was odd, then it would be 2 times the number of register plus 1. So 2 times 2 plus 1 is 5. Okay? And then the registers that are below the register we used now to output this new priority is reset down to 0. That's the construction. You may ask, why this? What does it do?
But the first move doesn't have an output. I'm a little confused now.
The first, I split. You can see it as one move, which I split into 2 just for explanatory purposes, but you can think of it as one move, right? So you get 2 inputs, the priority and the control,
I see.
which register to reset, and then you perform those 2 steps. Okay? Yes. So we reset all the registers below the one that we focused on, that the control told us to focus on. By reset, I mean we reset it down to 0. Okay? That's right. Yeah. So, what is it good for? How can we use it? Well, Karoliina handles that by a definition. What is the definition? She says, I'll say that a parity game G with some number of priorities has the register number K has register number register of G, okay? If playing the original party game with D priorities, and playing what she calls the register game, in which the checking, verifying the party conditions outsourced to that transducer if these 2 games are equivalent.
Where is this controlling?
So the control is given to the player who we want to win. Okay, so the control is in the hands of the player who wants to win in the game. And then Karoliina proves this remarkable result, which is that if you take a finite parity game, then the register number is bounded by the logarithm of the number of vertices. This has immediate algorithmic consequences because register game with k register is of size n times a number of priorities power the number of registers. This is a parity game in which the number of priorities is 2k. So using standard exponential time algorithms for solving parity games, we can solve this game in time the size of the game power the number of priorities halved. So we get this expression. Now, if we plug in log n, what do we get? We get a quasi-polynomial time. This is not quite state of the art. So even the first algorithm had better complexity. Was this? Okay, so there is a price to pay here. But I heard a colleague telling me, oh, this is actually teachable. And I was just curious. I mean, what is going on here? What is the register number? So together with Laure again and with Thejaswini, we, I believe, have managed to crack that mystery.
Is this DJT?
Laure Daviaud, me, and Thejaswini.
You know what is DJT?
What is it?
Donald J. Trump.
See you.
And you know he proved theorems. I don't think he knows what the theorem is.
So what is the theorem? The theorem is that the register number, this mysterious quantity that Karoliina has given it the logarithmic upper bound, is actually equal to the Strahler number. Who knows the Strahler number? Right. So Strahler number is a very interesting thing, right? So it originates from hydrogeology back in 1940s. A guy called Horton came up with a very muddled idea how to measure the complexity of a river network. You know, a river together with all of its tributaries. So that was just incoherent. But then Strahler, another hydrogeologist, actually formalized it rigorously enough. And then this number was rediscovered in computer science like dozens of times. For example, one of the first, I think, was Yershov in the Soviet Union, has discovered that if you want to evaluate, say, an arithmetic expression or any expression, then using as few registers as possible, then the number of registers that is sufficient, necessary, is the Strahler number of the tree of the expression.
There are two Yershovs.
Oh.
T and U.
So I don't remember which one. So what is the Strahler number? I owe you this. So if you have two rivers, baby rivers, at the root, they have Strahler number 1. When they meet, they have Strahler number 2. Now, if two rivers with the same Strahler number meet, then their Strahler number increases by 1. But if two rivers of different Strahler number meet, then the Strahler number of the resulting river is inherited from the higher one. This can be generalized to arbitrary trees, not just binary trees. Then you increase the Strahler number only if you have non-unique highest Strahler number of children. So what is the Strahler number of a parity game? We propose to measure the Strahler number of a parity game to be the Strahler number, the smallest Strahler number of its attractor decomposition. So since Moshe wants me to finish, let me just tell you another thing that I would like you to remember. And that is that last decade, the state of the art of solving parity games was roughly number of vertices powered the number of priorities. Now, thanks to the technology of so-called Strahler universal trees, the state-of-the-art complexity is number of priorities power the Strahler number. what next? So I have two hypotheses. What is a hypothesis? Right? It's something that you test empirically. So this needs to be tested properly. I think we have some, okay, we have some preliminary results which suggests those, but I think it has to be tested more robustly. So in the wild, the Strahler number of a party game is at most 4. 99% of benchmarks in Karen's collection have Strahler number at most 4. Party games with millions of vertices included. My second and maybe more provocative hypothesis is that in the wild, you can actually solve party games using these Strahler universal trees that I didn't have time to tell you much about, but you had an idea about their size from this thing to remember. It's actually sufficient to, you don't have to really treat n as a God-given number. You can consider this parameter, which depends on the number of vertices in theory, to be much smaller in practice and sublinear in the size of the game. Strahler universal trees should do the job. On the more theoretical side, I think that the Strahler number and the register parity transducer and the register number are interesting concepts that are understudied, and they deserve to be looked at in more detail. For example, in automata on trees. Thank you.